Good day and welcome to another physics lesson. Today we'll be looking at force between point charges. Under this lesson we'll be stating the Coulomb's law. We will calculate the force between point charges. I will also be explaining electric field intensity and electric potential, and then we'll be calculating each of these two quantities. So let's go on the journey. Let me start by explaining what we mean by point charges. Recall that under our current electricity lesson in Ohm's law, we said that electric current is the rate of flow of charges. So we have flowing charges or moving charges causing current or producing current. But in this lesson, we are focusing on point charges. That means static charges. Static that are more or less stationary at the points where they are. Charges whose movement is limited and whose movement is only from one point to another, from a specific point to another, as against the charges that are flowing continuously in a circuit that produce electric current. Also, you'll recall from our previous lesson that we already said that the region around the charge where the electric force due to that charge can be felt is the electric field. For better explanation on that, you may also refer to the previous video also on this YouTube channel. There is an electric force between 2 point charges. As a matter of fact, there is always some form of force between two objects. If it's not an electric force, it could be a gravitational force. If it's between two masses, we have a gravitational force. But now we have two charges. So there's an electric force between two charges. And Charles Coulomb, who lived between 1736 to 1806, was the one who first of all worked on this and propounded a law called the Coulomb's law. This Coulomb's law describes the relationship between the force between 2 point charges and the charges themselves. And so what does Coulomb's law say? It just says that the force between 2 point charges separated by a distance is directly proportional to the product of the charges and inversely proportional to the square of the distance between the charges. So essentially, Coulomb's law is saying that if you have 2 point charges, let's say 2 electrons, the force between the two charges, or 2 electrons if you like, is directly proportional to the magnitude of the product of both charges. So that means that if you multiply the magnitude of the two charges, the higher the product you get from that, the higher the answer you get from that product, the higher the force between them. But it also goes on to say that it is inversely proportional to the square of the distance between them. That means that if you increase the distance between charges, then you would have also reduced the force between them. Which makes sense because the closer objects are together, the more effect they are likely to have on each other. So the closer two charges are to each other, the more the force they are likely to exert on each other. So if you reduce the distance, if you reduce the force between them, meaning that you have increased the distance between them. So if you increase the distance between them, then you have reduced the force. Increase distance, reduce force. Reduce distance, increase force. But if it comes to the product of the charges, if you multiply the two charges by themselves, the higher the answer you get, the higher the force. So that one means that the higher magnitude of the product of the charges, the higher the electric force acting between them. Let us look at the mathematical representation of Coulomb's law. The first thing he said was that the product of the two charges is directly proportional to the force, and that's F proportional to Q1, Q2. And then he said that F is also inversely proportional to the square of the distance between them. So if you do this joint duration, you have F is proportional to Q1, Q2 over R squared. Of course, whenever you have a proportionality sign and you want to change that sign to equals to, you have to introduce a constant. So in this case, we also have a constant K, and our K is also equal to 1 all over 4 pi epsilon naught. Epsilon naught is a term, is a symbol that stands for permittivity of free space. Permittivity of free space. Permittivity is a term that describes how different materials allow electrons or allow charges to flow through them with respect to vacuum. The ratio between the rate of flow of materials, or rate of flow of charges in materials with respect to vacuum. That's what permittivity of free space essentially talks about. So if we now are able to put our 1 over 4 pi epsilon naught into that equation for F, that means that we Q1, Q2 over 4 pi epsilon naught R squared. And as it is with all charges, like charges repel, unlike charges attract. So if your Q1 and Q2 are like charges, then you will have a force of repulsion, you will have a repelling force. But if they are unlike charges, you have an attractive force. So if Q1 and Q2 are, say, an electron, then they will repel because an electron carries a negative charge. They are both like charges. But if it's an electron and a proton, there will be an attractive force between them. So let's see the solved example. They are asked to find the force between two protons. The value was given. All you need to do is to just do your calculations. F equals K Q1 Q2 over R squared. Now, many students make a mistake of not squaring that R. Many students, they write the formula Q1, Q2, K Q1 Q2 over R squared, they write it correctly, but when it comes to their calculations, they don't square the R. So they just put 5.3 times 10 to the minus 11, for instance, without the square. That is a very common error. Please, you have to be conscious enough not to make that error. The R must be squared. The R must be squared. And of course, that R must be in meters. This question already gave it to you in meters, but in case you find a question that gives it to you in centimeters, you must convert it to meters and then square it before substituting it for R. Please take note of that. So in this, if you try to solve this also by yourself, you'll find that the answer is 8.2 times 10 raised to the power minus 8 newtons. Now let's go on to look at electric field intensity. Whenever you hear the word intensity, a synonym for it is strength. Intensity, strength, how strong something is. That's what intensity means. So when we say electric field intensity, we are only referring to how strong an electric field is. How strong an electric field is. That's what we are talking about. So how do we measure the strength of an electric field? It is given by the force per unit charge. So what is the magnitude of the force that is exerted per charge in that field? So of a unit charge in that field, what value of force will that charge experience? That gives you the intensity of that field. So E equals F over Q. And if E is F over Q, and we know that F is a force, that means it is measured in Newton. Q is a charge, meaning that it's measured in coulombs. Then our units will be Newton per coulomb. Per standing for the division you have in the formula. So electric field intensity E is measured in Newton per coulomb. If you make F the subject of that matter also, you'll find that F is equal to QE. F equals QE. Now let us not forget that our F is Q1 Q2 over 4 pi epsilon naught R squared. Let's not forget that. So if we substitute that for F in our formula for E, where we have E equals F over Q, if where you have F, you put Q1, Q2 over 4 pi epsilon naught R squared and do your substitution, you'll find that one of the two Q's on top will cancel one Q below. So that gives you Q over 4 pi epsilon naught R squared. So that means that also an electric field intensity could be given as Q over 4 pi epsilon naught R squared. And also let us not forget that 1 over 4 pi epsilon naught is K. We already said that earlier. K is 1 over 4 pi epsilon naught. So if you substitute that also, we can simply say that E equals KQ over R squared. So at the bottom there, I deliberately wrote those formulas out again, so that depending on what you have, depending on the quantities you are provided, you know that E can either be F over Q, or you can say E is Q over 4 pi epsilon naught R squared, or you also say that E equals KQ over R squared. It will be good for you to know all three so that you don't get stuck anywhere. Here we also have a solved example where we are asked to calculate the electric field intensity in vacuum at a distance of 10 centimeters from a charge of 5 times 10 raised to power minus 4 Coulomb. As we said earlier, our formula is KQ over R squared, and K is a constant. K is a constant whose value is 9 times 10 raised to power 9. So you just substitute that, put the value you have for your charge Q there, and your distance. You will see here that I have converted my distance from centimeters to meter. I had 10 centimeters in the question, but I converted it to meter, making 0.1 meter, and I didn't forget to square it. Please do not forget to do likewise. Now let's go on to electric potential. Now wherever you have an electric field where you have forces acting between them, whether force of attraction or repulsion, you have to do some work to be able to move a charge against this field. You already have a field. There's a force in that field. So if you want to move a charge from somewhere into that field, you must do some work, because you must be able to overcome that force. You must be able to overcome the force in the field already. It's like you trying to break into a house, for instance, a heavily secured house. You have to apply some force to break through the door or through the wall. So in this regard, we are saying that you must do some work before you can bring a charge or move a charge into an electric field. Now this work that you do is what is called the electric potential, and the symbol is V. It has the same symbol as voltage or potential difference or EMF. They all have the same symbols, V, because in a manner of speaking, they are very, very similar. Not quite the same, but very similar. What then is electric potential? It is the work done in bringing a unit positive charge from infinity to a point in an electric field. You are bringing something from outside, inside. Then you have to do some work to move it. So if you consider 2 points A and B in an electric field, the 2 points A and B are in an electric field. So if you now want to bring a positive charge from outside the field, if it takes you more work to bring that charge to A than it takes you to bring that same charge to B, then that means that A is at a higher potential than B. Because you want to bring something to A, someone else wants to bring another thing to B. The person who brings something to A does more work than the person who brings another thing to B. What it means is that A is at a higher potential. That thing in this case being the charge that you are bringing into that field. So A is at a higher potential than B. Now between A and B also, that means between even two same points in an electric field, the same field, but we have two different points there. Two same points in an electric field will not have the same potential, except the points are at the exact spot. So when we have an electric field and you have two different points in that field, the two different points will not have the same potential. Now, the difference between them is what is called potential difference. Potential difference is different from electric potential because potential difference has to do with difference in potential between points that are already in the electric field. But electric potential has to do with the work you have to do to move something from outside and bring it into an electric field. That is the difference between electric potential and potential difference. Both the electric potential and the potential difference are scalar quantities. Both of them, they are scalar quantities, meaning that they do not have specified directions. They are only magnitudes, and they are measured in volts. Now, we already said also in our previous lesson, one of our previous lessons, where we looked at electrical energy, we said W equals QV, where our W is work and V is the potential difference. So if we also import that formula here, we will have our V being equal to W over Q. So what that means is that your electric potential is equal to the work done divided by the charge that you are moving. Also, our V is also given by E times D. Remember that E is our electric field intensity, which has the formula Q over 4 pi epsilon naught R squared. So also, if I substitute that into that formula, V equals E times D. So where I have E, I put Q over 4 pi epsilon naught R squared there, bearing in mind that both R and D means distance. R stands for distance, we got that from Coulomb's law. D also stands for distance, we have already known that all along. So, bearing that in mind, then my V will be equal to Q over 4 pi epsilon naught R squared, everything multiplied by D. Now, since D and R are both distances, that means one of these distances as the denominator can cancel the D, and then you have Q over 4 pi epsilon naught D. Some instances you will see Q over 4 pi epsilon naught R. It means the same thing. D and R are distances. So if not D, it will be R. So the formula for electric potential also, we have arrived at 3. We have the first one, work done divided by charge. We have the second one, electric field intensity multiplied by distance. And then we have the third one, the charge divided by 4 pi epsilon naught D, where D stands for distance. Let's also look at some solved examples under electric potential. You are given the question, there's a voltage of 40 volts, a distance of 10 centimeters. You are asked to calculate the electric field intensity between them. So in this case now, we are looking for electric field intensity. But because of the parameters that I have, I did not have the charge. Neither was I given anything that has to do with K. So what formula can I use? That's the simple formula we just saw from electric potential. That's V equals E times D. Since I have V and I have D, all I need to do is to make E subject of my formula. Not forgetting that the D must be converted to meters. So if you do that, you get 400 volts per meters. Now, if you are wondering that earlier we said Newton per Coulomb is a unit for electric field intensity, and now we are using volt per meters, both are correct, depending on the parameters you have worked with. Here, I have worked to get E by dividing V by D. V is voltage measured in volts. D is measured in distance. That means we have volt over distance, volt over meters, volt over meters. That is volt per meter. That's where this unit volt per meter was arised from. But it does not mean that if you do another question and you solve by using, say, F over Q, and you get Newton per Coulomb, that you will be wrong. No, you are not wrong. Now, this other one is for you to lay your hands on and try. Calculate the potential at a point 40 centimeters from a charge of 3 times 10 to the power minus 6 coulombs. Here, if you do this, you will get the answer that I put there in brackets. This is still the same method. You are asked to calculate the potential at this point. That means you are looking for V, and you are given the distance, you are given the charge. That means you have to use the formula for V that has to do with distance and charge. So on our previous slide, you will see how we do that. That would have given us KQ over R, or KQ over D if you like, and then you'll get your answer. So here we come to the end of the lesson on Coulomb's law and force between point charges. I believe that you'll find this lesson useful. Here again we have questions that it will be good for you to lay your hands on. K, as I said, is a constant. It's usually provided in any examination you write. The value is usually provided. So where necessary, all you need to do is to apply K, the value 9 times 10 to the power 9, wherever necessary. So solve these questions for you to practice what you have learned in this video. And if you do have any problems, any complaints, please feel free to contact me via my YouTube channel. I'll definitely be willing to help. I'll be there to reply your comments or your questions. So thank you for being a part of this lesson. Hope to see you very soon in another lesson. Feel free to subscribe to my YouTube channel. I am David Oluwadara on YouTube, so that as new videos come on, you will be notified and you continue to enhance your learning. Thank you.